Now that we've learned the chain rule, now we have the power to tackle some functions that up until now we couldn't really do. So we did prove earlier that the derivative of e to the x is itself. That was pretty exciting. So let's take that fact, all right, along with this other fact. The exponential, the natural exponential function base e, and the natural log function base e, when composed together in this way, like you here sticking the log inside the exponential, they actually cancel each other out because they're inverse functions. This is an example of like f of f inverse of x giving you just x back. Or in this case, I called it a because it might not be x, it might be just a constant. So composition of inverse functions, they cancel each other out. So that means anytime you have a number that's not e, you can actually write it like this. So with that in mind, see if you can pause the video right now and see if you can figure out what the derivative of 2 to the power x is. I think I'll go ahead and walk through it. Tell you what, I'll give you the answer first, and then I'll show you how it's done. So you can check your answer, and if it's wrong, you can go back and see if you what you can do. The answer should be that derivative of 2 to the x is 2 to the power x times the natural log of 2. That might not look exactly like what you've got, but it might be equivalent. You might have to use this rule again to fix it. All right, so I'll go ahead and walk through how this works now, the proof. And the way we can do it is to say, well, first of all, 2 to the x, if I want to do its derivative, that's the same as saying the derivative of e to the power natural log of 2, which equals 2, all right, by this rule over here, and then to the power x. Now, if you have a power of a power, then you can multiply those powers together. Like you can simplify that. That's another one of those exponential rules. Like e to the power a to the power b is just e to the power a times b. And so we can do the natural log of x times 2. I'm actually going to write, let's write it that way. Natural log of 2 times x, like that. Okay, so I haven't actually done any derivatives yet. I've just been messing with the original function to put it into a format that is going to be easier to work with. Now that we have it here, now we can perform this derivative using the chain rule. This is a composition. We have e to the u on the outside, and then we have natural log of 2 times x on the inside. Now the derivative of that is not actually hard. You might think it looks hard because it involves a natural logarithm, but what's inside the logarithm? It's just 2, which is constant. So this entire part right here, that natural log of 2, is constant, which means all we have here is a constant multiple of x. That function inside there is linear. Not hard to take a derivative of. You don't need to know how to do a derivative of a natural logarithm yet. We will learn about that very soon, but we don't need that yet. So all we're going to do here is the chain rule, the derivative of this. First we apply the derivative of the outer function, which, because it's the natural exponential now, is just going to be itself, okay, with the original inner function still there, and then we'll multiply by the derivative of that inner function. But since, as we said, that's just a linear function, its derivative is just going to be the coefficient, okay? It's just like the slope of the line, which is just the natural log of 2. So now we're almost there, because we can separate this back out again, e to the natural log of 2, and then that to the power x, and that, just like we did before, just like we did in this step, that part's just equal to 2. So let's put this back in terms of the 2 to the power x times natural log of 2, and that's how you get your answer. So in general, this generalizes to a general rule where the derivative of a to the power x for some a greater than 0, okay, any positive number a, is going to be itself natural a to the x, and then times the natural log of a, just as a constant multiplier. So this means that whenever you have exponential growth, if the base of your exponential function is not the e number, if it's some other number like 10 or a half or whatever, then the rate of change in that function isn't exactly equal to the function, but it is a constant multiple of the function, where the constant multiple is the natural log of the base. And so that means that this is showing with calculus that the exponential functions have a rate of change which is proportional to their value. Which was kind of the big exciting thing about about exponential functions that I talked about the other day. And that's what makes them really useful for modeling things like all the things I mentioned. What was it? Like population growth and radioactive decay and continuously compounding interest, that sort of thing.